Okay, hello guys, I will try to show you today how to debug the Dragon's Dogma online client. So to do that I developed some code here that can kickstart the client and provide a dummy response. To do that you just get this project from GitHub. You need to provide some arguments depending on what you want to do. If you want to start the server, you need to provide server start. If you want to decrypt, you need to just write the decrypt argument. So we just start the server for now. You can use any IDE you want for this. Um, Once it starts, it should say like startup result is true. You want to set the breakpoint before it being sent, just to be sure that you actually hit it. So what the server does, it will answer all the client's questions, and as soon as the client connect, it will call this method and it will actually send some initial data, which is just some hard-coded string, hard-coded response right now. So the server is running. We start the client. For the client, you want to have the scalar height plugin with the following options here. You can create a new profile and then tick the boxes just as they are ticked here. And then you also want to provide the command line arguments. You want to provide the local host for the address and the correct port. Token and doesn't matter, and for download you want to be sure to provide this URL that will ensure you hit the server. And then when you're ready to go, you want to make sure that you disable all your breakpoints, because if the breakpoints are enabled before you run the client, he might be detected and might just back out. I have a few breakpoints here, but really you only need two, which is the receive method when the client receives data. Right now if I go there you actually cannot see anything, because the client will only reveal its code I think after you run it. So I think it unpacks during runtime, I'm not too sure, but I haven't spent time investigation and it really doesn't matter for discovering the decryption method right now. And the other important breakpoint will be for the XOR operation of the first byte. So this is actually where the decryption routine starts. Alright, we have all set up, so we just press play. You want to be sure that you press play in a timely manner. It might happen that the client crashes the first or second time, is a bit not so stable and very prone, or doesn't really like to be debugged at all from my experience. So it's running right now, but you will notice it will hit some stops, like it will have some fake trap breakpoints here. You just try to continue in a timely manner until you reach the title screen. It might crash at any point, and then we just retry. Let's see if we get it by the first time. Just keep pressing play, and then when you're in the title screen you want to wait for one more stop, and then you want to quickly press game start. What happened now is you will have hit the breakpoint here before it's being sent. You want to activate your breakpoints here for the receive. So I enabled this one now, so whenever we receive something it will stop the client, and then we just send this packet off, fly to go, and then we continue our client. And now we see we hit the receive breakpoint here, and you can see the code is more clear now. And you also want to go to the XOR for the first byte and enable this breakpoint here, and then we will just continue the code until we find our data in the receive buffer. So the receive buffer is located at this position. We can follow this value. We step over this receive method and we see our data is in the buffer. So this is like the data that the client just sent. It starts with 0130, which is the packet header, and then it will have the client data with COFA starting here. So we have the same here, packet header COFA, and then it will end somewhere at 37A7, which is here. So this is the data which we just sent to the client. And where's the start? I missed it here. Right. So this is actually the payload we just sent to the client. This server has no purpose anymore right now. So we just continue and wait to hit our other breakpoint, which is the XOR of the first byte, which is not enabled. We definitely want to make sure that we enable this breakpoint before pressing play. Receive buffer, so this one, oh, I don't need any more. This receive, I also don't care anymore. This one, no, was a mistake. So we only need the XOR of the first byte, which is here. We press play and then we will hit the decryption method. So this is where the client will decrypt the data, and if we follow the ACX register in the dump, we will see that it points us to the beginning of the data. It will start with CO, so these are the first 16 bytes, COFA, which is basically the payload of the package. So we can just close the server right now, we don't need it anymore. It serves its purpose. And what we want to do now is we will follow along with the decryption method, which I implemented the decryption method in the decrypt command here, which will be called automatically if you provide the right argument, which is the decrypt argument. Is basically just decrypt. And what it will do, it will run this method here. It will basically provide the exactly same data which we provided to our client, and it will emulate the decryption method. We can set a breakpoint here at the decrypt, which will be called with this data. So we just run this right now. And we will create a buffer. This buffer will just help us to read some data and stuff, so it's not really important. So what's important is the operation is it will read the first 16 bytes, which is this one from CO to D932. So we mimic this, we create a data array with the same data, CO to D932, and then we call the process 16 byte method, which is here. So we continue to go here. It's basically just preparing some stuff. Now at the beginning I reordered a little bit around till here. I think all these commands a bit out of order, but after it should follow closely with the assembly code. So in a sense what it does, it reads a value, it reads a key, and then XORs those things. If we step a little bit over it, set a breakpoint here. So now it performed all these calculations already, and now we follow the assembly code and just show you how it's done in assembly, and that these calculations are the same basically. Okay, so what we do here is we XOR the value from the ECX register, which is basically this one. It's B476FACO, which represents value A. So if we check value A here, is the same, B476FACO, and it will XOR with the EAX register, which is the key, which has been loaded in the previous code, which I didn't show it right now. So if we check the EAX register, it's F3C4 blah blah. Is the key which will be get from a lookup. So the key A is F3C4137E, which matches this one. And then it will perform the XOR operation. Here in the comment you can see actually the exact code, the exact address of the assembly code. So it's B18539, and we see here's the same line, B18539. So it's very easily to find the operation performed in assembly in this code here, even if it's quite messy. So we expect the result to be 47B2E9BE. So if we step over this here with F7, we expect EAX to have that value, this one. And then now, okay, we do the step, EAX register is 47B2B. Yeah, it's basically the same value. So the calculation we did here is the same as the client performed here in the assembly, and it will do so with the first 16 bytes, so 4 byte, then the 8 byte, 12 byte, and then here is the remaining. Yep, and then it will basically later come to this loop. So I'll just step through to get to this loop. So we hit F8 a couple of times. You see it has a lot of jumps to confuse us. It's quite annoying. So let's just go with this. So what this does is the finishing. It will jump around now. It will push this address 19927DD, which I remember in the jump variable here, so later we know where we jump. So because the jumps are always a bit different, I just compare them. If you jump to this address, you need to execute this code, and so on and so on. There are quite a few jumps, and it uses this jump address a lot. It's basically, each of them should probably be their own function, and the code just got mangled into the state to use jumps. So I just follow along with it for now. We can optimize this later once we actually have figured out the whole routine. So after it pushes the jump, it will just go, and I made a comment here only for myself. It's basically the start of the loop. The start is a loop method. It will be called multiple times before a single result is returned. So I just hit the breakpoint now here at the end of the loop before it jumps around. So now we have all these calculations already performed, and we will follow along with the assembly. Now, as I mentioned earlier, this code in the beginning is not close to this one here, so I will just stop at the XOR for the time being, and then later tell you when it's more accurate. So if you step with F7 through this, we have our first XOR method here, which is located at 3B something, so you can just copy the address and find it here. So this is this XOR operation here, and the result should be 9A, and what's being XORed is BE with 24. So we check EAX is 24 and ECX is BE, so those values match up, and then we see if the result is the same. We press F7, and ECX is 9A, is basically the result which we predicted here, 9A. Alright, and then let's keep moving. So here's the next XOR. Let's see where I put this, because as noted, it's a bit it's not in order. I will tell you, you will see it will be in order later. So now we expect to XOR E9 with 30. So ECX is 30, E9 and ECX is 30. So we perform this operation, and ECX is D9 now, and we predicted it to be D9. Right, let's keep moving. I think it might be in order right now. Let's just see to the next XOR. Copy address and find the address in this messy code. So now we XOR B2 with B3. So ECX and EX B3 with B2. Step over this. Result is 1. Our result is 1. Great. So the next address is 24639F4. 39F4. Is this? Yeah, I think right now we are good to go. So these first blocks, they're exactly doing the same as the assembly, but we move them a little bit around, which maybe not be too good. Anyways, what this line does now, it looks something up from a static table. So it uses the XOR result, which was 1, to look something up from a table. The table is located at the address 2179DDO. So I just call it in the code 2179DDO, and then if we basically follow in dump the constant, we will go to the beginning of the static data. It's 782, and this static data is here, k blah blah is 7082 2c. It's the same data block here. Let's get back to our code wherever we have been. Yeah, I think we've been here. So from this blob of data, we now look up the result of the last XOR operation, which is 1. So ECX here is 1. So with the addition 1 plus this, it will basically point to the address ECX 1 plus this thing, which is A2. So we look this up from our implementation. Shit. It's already been looked up, it's already been calculated. I shouldn't press F7, now I have missed this. Here. So it is A2. And now if we step over here, the RL register thingy, I have a nice image here. RL is the lower of the EAX. So it will be, we step over, and this B3 should be the result of this table, which is 82. And we have the same here, 82. We look it up from the first index of the static table, and we also have 82. What happens next? The next instruction should shift something to the right by 1, the result of another operation. So let's see what the ASM code does next. It moves some registers around. Move, I don't need the move here because I have a, you can see I have a variable for every operation, so we don't really need to move around shit. And we shift right the AL, basically the 82 by 1. What do we do here? 82 shift right by 1, and the result will be 41. So we step over it and it's 41. And then the next thing is we will shift something to the left by 7. We shift the same result, which is 82, to left by 7, and the result is 0. So now it shifts the CL, which if we get our handy picture, CL is the lower register of ECX. So CL currently is 82. You remember the move command it did before? If we go back a little bit, I can show you again. So basically this move did nothing else than copy the 82 from ECX to CL, so we have it duplicated. And it then shift one of those, the EAX register, to the right, and the other one will be shifted to the left by 7, so it's the ECX, the 82, and the result will be 0 as calculated by us here. So we step over this one, bam, the result is 0. And then those results of AL and CL will be XORed, which is implemented in this line. So you see the 41 and the 0 will be XORed, and the result will be 41. Surprise. We press step over this, and CL will have no modification. It will just stay black or red because it will not change in this step. It will? Alright, it will, because it's 41, sorry, but as we predicted. And oops, so this just goes on like this, so all this code that runs here is basically the same like programmed here. And that's basically how you can follow along and perform the decryption routine. And I know it's not complete, I mean it does all this stuff with the data, and after it all did this, it calls another method to do even more transformation, which I haven't investigated yet. And yeah, I think that's the next step to do, just follow along with this decryption method and see how the final data will look like, and get a way to emulate this behavior so we have the same final data. And that's it. I hope it helped, and I hope it helped you to get this thing rolling. Bye bye.